Jagiellonian University in Krakow, Poland. And the title of his talk is Topological Models of Zero-Entropy Loosely Bernoulli Systems. So
Okay.
thank you, and when you want.
Yeah, thank you very much. It's great to be. It's great to be invited to such a nice event. It's a pity that we have to do it online. I have to say that attending a conference online and at the same time teaching and maintaining a normal professional activity is extremely hard, and that's the worst part probably about that when you are visiting a place you can totally immerse into a conference, while
Yes.
once you are doing your normal teaching and um, other things, it's much harder to attend all the talks. So I would like to apologize to all the speakers whom talks I have missed because of that. Anyway, so let me start. Please feel free to interrupt me at any point if I will be talking about things you don't know, because my talk will be a little bit different than talks that were announced here so far. So I my setting is this very general setting of topological dynamics. So X denotes a compact metric space. D is, or maybe, I'm sorry, rho is a metric for X. T going from X to X is continuous, is a continuous map. Is a continuous map. So a very general question one may ask about this situation is how to measure distance between orbits, because we know well that the metric rho, it actually measures the distance between points, but the distance between 2 points doesn't tell us much how the future evolution of those 2 points will look like under the action of our discrete dynamical system given by T. So we all know, and this is one of the favorite topics in topological dynamics, that we see things like sensitive dependence on initial conditions. We see things like that. The 2 points which are very close initially may exhibit future evolution which is very different. But they are situations in which we would like to still know that those 2 points give us the right the orbits of 2 points are still close, and we would like to measure that and see the consequences. Of course, the question is, okay, why we would like to do so? And there are many answers to that question, but if I will be talking about those answers, I won't be able to describe the reasons I would like to describe. So they are, please, you have to take it by my word that they are situations in which you can use these measurements to prove something about interesting systems which are not artificial. But right now, let me just point out one possibility of measuring this distance. This is called Besikovich pseudometric. And well, it is denoted dB, and the Besicovitch pseudo distance between 2 points is equal to the lim sup as n goes to infinity of averages 1 over n, j equals 0 to n minus 1, rho tjx tjy. So here is an example of a pseudometric I announced earlier. Now we are really measuring not only the initial distance between points, but we are capturing the evolution of the distance between points on the orbits of x and y. So we are just, what we are doing is that we are now applying our, so that should be t of y, t of x, t square of x, t square of y, etc. We are now applying our dynamics, then measuring those distances and taking the average somehow, looking how the average distance look like after the first n iterates, and looking into lim sup of that upper limit of that sequence of averages. So in this way, it may happen that this is a pseudo distance between, because this function is certainly symmetric. It is easy to see that the triangle inequality will still hold, but we will lose definiteness. So it may happen that for two different points, this Besicovitch pseudo distance will be still 0. So this is just a pseudometric, but well, another maybe even more naive way of measuring distance between 2 points will be like t sup of xy, and this will be just given as, say, supremum over all n greater or equal than 0, rho tnx tny. So we are looking at two orbits, and we just take the smallest upper bound for all those distances we see along those two orbits. And this we put as a measurement of our distance. This will also usually, okay, in both cases, we usually just see functions which are not necessarily continuous with respect to the product topology on the space x times x. But those functions also allow us to distinguish certain classes of dynamical systems. So if I do the following, if I put the following definition, a topological dynamical system xt, so this pair consisting of compact matrix space and continuous transformation, is equicontinuous if for every epsilon greater than 0, there exists a delta, which is also positive, such that if we have 2 points rho x and y with an initial distance smaller than delta, then this supremum distance between those two metrics will not be larger than epsilon. So this is a definition stated using this metric d sup. It is usually stated that the family of iterates t to the power n is a equicontinuous family of functions, but I would like to stress that this definition, we would like to look at the definition as a definition which says that, okay, I have a dynamical system, and the dynamical system has a naturally defined function between orbits, and this naturally defined function between orbits turns out to be continuous with respect to the initial topology. And it turns out that this condition of continuity, this continuity condition, nicely distinguishes a class of dynamical systems called equicontinuous dynamical systems. And by a theorem of Halmos and von Neumann, one can actually prove that this kind of systems has to be modeled as a rotations of compact topological metrizable groups. And so an example of an equicontinuous system would be an irrational rotation, or any rigid rotation of the circle is an example of an equicontinuous system. And there are many others which share this situation, that there's an invariant metric, and actually the phase space can be endowed with compact metrizable group topology. So this was a long known fact about those systems, and the name itself is not that old, but the definition is old. So a topological dynamical system XT is mean equicontinuous if, again, for every epsilon there exists delta greater than 0, such that the distance rho xy smaller than delta implies that Besikovich pseudometric xy smaller than epsilon. And of course, we have that every equicontinuous system must be mean equicontinuous, but not the converse is not true. And well, the class of those systems was first studied by Sergei Fomin in the 1950s, the 50s of the last century. And but this condition and this pseudometric given by Besikovich appears so naturally on many different occasions that some results in this area were rediscovered by many people on multiple occasions. But here we have a nice class of mean equicontinuous systems, and it turns out that those mean equicontinuous systems, they still give us, well, this mean equicontinuity condition implies some strong consequences on the set of all invariant measures. So in particular, if I have a transitive mean equicontinuous system, then necessarily this transitive mean equicontinuous system has to be minimal and has to have only one ergodic measure. And so transitive uniquely mean equicontinuous systems are uniquely ergodic. And one can show that actually this unique ergodic invariant measure carried by that minimal system has to be isomorphic as a measure preserving system with the compact group rotation, and such compact group rotations, they preserve the Haar measure. So, and this is there's an isomorphism, not necessarily topological, but on the measure preserving level, those kind of systems are still the same. So so we have this kind of condition. So I hope I convinced you that it makes sense to study those metrics or pseudometrics on the phase space of a topological dynamical system which measure distance between orbits, and conditions giving you kind of a stability between the original metric and this new measurement of orbits are useful in the sense that they allow to distinguish and describe certain classes of dynamical systems in a like intrinsic way. So let me also introduce some more notation. So MTX, let this be set of all Borel T invariant probability measures. Let MAET of X be the set of all members of the set of all T invariant measures which are ergodic. And now definition. We say that a topological dynamical system X, Y, S, so compact metric space Y together with a transformation S, is a topological model for a measure preserving system X with a sigma algebra Cayley X measure mu and transformation, measure preserving transformation T. So this is a little bit conflicting with my previous notation, but so we have that a topological system is a topological model for a measure preserving system if the system from X to X, if the set of ergodic as invariant measure on the space Y is Borel measure consists of single measure nu, and the systems X Cayley X mu T and the system Y By denoting Borel sigma algebra nu S are isomorphic. So being a topological model means that you look at the measure preserving system. So measure preserving systems are not necessarily given by a continuous transformations on a compact metric spaces, but you look at the measure preserving system, which you have to assume that it is defined on a decent measurable space. This part I would like to sweep under the rug for a moment. So if I have a decent measure preserving system, then I can always, without losing anything, any information about my measure preserving system, I can assume that this measure preserving system is actually given by some continuous transformation on the compact space. So every ergodic measure preserving system has a minimal topological model. So this is known as a Jewett-Krieger theorem, and there are also strengthenings of that theorem, telling us that you can actually also assume that this topological model is actually topologically mixing. But those results are due to Benji Weiss and his collaborators. So we always know something about those topological models, and look, yeah. One can observe that condition like equicontinuity tells us that the system we are observing is a topology. Well, if I have a minimal equicontinuous system, then it has to have a unique ergodic measure, and it turns out that my equicontinuous systems considered as a measure preserving system is actually isomorphic to an action of a group rotation on the compact topological group, which preserves R measure. So equicontinuous. Yes.
Just one question just to be sure to be honest. Do you assume here that your space Y is a metric space?
Yes.
And S is continuous.
Yes. So saying that
that's the definition.
That topological dynamical system is by definition a pair YS such that any pair consisting of a space at the transformation such that the space is a compact matrix and metric and transformation is continuous. Thank you for clarification, Jerome. Yeah. So this is what we are doing. So finally, after this long motivation and introduction, I would like to announce my yes.
Sorry for interrupting. Just because
No.
before you start with the next part, basically, I wanted to ask, you just said that in the Jewett-Krieger you can have that the system is weakly mixing, right? So basically,
even strongly mixing.
Strongly mixing even. So what I just asked myself is, if you start with a mean equicontinuous system, then you always have basically also a topological model which is equicontinuous. And you also have a topological model which has the strong mixing property. So these kind of, I mean, usually such systems are disjoint.
Not necessarily disjoint, but we certainly we certainly have those situations. Like if I consider like a rotation of the circle, right? Mm-hmm. Any rotation of the circle by an angle alpha can be considered as a like T1, Borel sigma algebra on T1, and Haar measure denoted maybe by lambda and rotation, right? This gives me a measure preserving system. Mm-hmm. And I can have, and of course, because I started with something continuous, so this rotation, it is its own topological model, mm-hmm. which is equicontinuous. Okay, but a well-known example asks you to like pick an interval. If I now pick an interval of length alpha and take the characteristic function of that interval by just creating a sequence of zeros and ones corresponding to the orbit of a point 0 in such a way that whenever r to the power n of 0 enters this interval, I write down 1, and otherwise I write down 0. Then I will obtain a symbolic 0-1 sequence, which is called a Sturmian sequence. And then I will obtain a mean equicontinuous system, which is nevertheless not equicontinuous, but this will be mean equicontinuous and won't be topologically mixing. Okay? And then we have another thing, which is like the Jewett-Krieger theorem version by Weiss, which says that, okay, you can also construct a topologically mixing model for this measure preserving system, which necessarily will be something different than those two models mentioned before.
Yeah, no, I was just surprised because you are measure theoretically equivalent, but on the topological side you have some very different behavior, right? This strong mixing versus equicontinuity. This is just a bit surprising.
Yes,
cool.
but okay, one should always remember that being isomorphic on the level in the category of measure preserving systems is a very strange thing, because say up to isomorphism we actually have just one measurable space.
I see. Yeah.
So this is unit interval with the Lebesgue measure, and this is a model for every such space. So this tells you immediately then all those isomorphisms in the measure theoretical category, they have to be quite strange and very far from being regular in any topological sense maps, because yeah, so those things happen, and this is something which can happen in and appear, and then
Okay,
okay.
Thank you.
So let me just we have now another, so together with Felipe Garcia Ramos, so those would be joint results. Felipe Garcia Ramos. So he's in San Luis Potosí in Mexico. So we looked at class of dynamical system, which is characterized by yet another dynamically defined pseudometric. So in order to define this dynamically defined pseudometric, I have to work a little bit, but so first definition tells that for points x and y in X, and n delta match is a function I which goes from some domain to some range, such that the following conditions are satisfied. The domain of this function and the range of this function are both contained in the set of integers from 0 to n-1. Pi is order preserving bijection, and for every I in the domain of pi, I see that the distance between Tix and T of I y is smaller than delta. So in other words, I have on the picture, it might be easier to see what's going on. I have orbit of one point and I have orbit of a second point. But now I'm looking for a function which pairs up points from one orbit with points on the other orbit, but does not necessarily, maybe I should, it is not necessarily a function which is like order preserving. I just looking at the two orbit segments of length n, and I try to find as many pairs of points at the distance smaller than delta as possible, given that my pairing function will keep being an order preserving function. Okay, so I do not permute my orbit segment arbitrarily. I'm trying to for that orbit segment to pair up to them to being order preserving. And now I define a function which I can denote as f bar n delta xy, and this is actually equal to 1 minus maximum of the cardinality of a domain of pi, where pi is an n delta match. So the bigger cardinality of a match I can find, n delta match I can find, the smaller f and delta becomes. And finally, I do the two usual tricks. So first I pass with n to infinity, and then I define the quantity f upper bar delta xy equal as lim sub as n goes to infinity of f n delta xy. And finally, I define a function rho fk xy as the infimum over all possible deltas, such that f bar delta xy is smaller than delta. So this definition it is maybe complicated, but it is motivated by so-called edit pseudo distance between symbolic sequences. And if you try to find out the topological equivalent of that definition, which works in general, not necessarily only for systems which are symbolic, then you end up with that definition. And one can prove that actually this is a pseudometric. It gives us a notion of a pseudo distance between orbits, and you can define the systems. We say that a topological dynamical system xt is rho fk equicontinuous if we have the following: for every epsilon there exists a delta such that if 2 points are at the initial distance smaller than delta, then this rho fk distance between those two orbits is smaller than epsilon. And again, I would like to stress that the definition of this pseudo distance was not taken from a thin blue sky. So it was not like that we were looking how one can generalize Besikovich metric, but we knew that there are examples when Besikovich metric is not good, but the orbits behave in a way such that removing smart parts of those orbits, the remaining points can be paired up such that they stay close. So trying to capture that leads to something which one can observe as similar to this edit pseudo distance, and then one ends up with this definition, and it turns out that this pseudometric can be useful because if you, for example, show that a sequence of generic points converges with respect to the rho fk, then you can conclude that this limit point will be also a generic point for some invariant measure. And if your sequence consisted of generic points for ergodic measures, then your limit point will also a generic point for an ergodic invariant measure. So many, this pseudometric has its applications which are independent of what we were doing, but Felipe and I, we just asked, okay, what this condition of rho fk equicontinuity means for a dynamical system. What can be said about that? So I need one more definition, and this definition is about measure preserving system. So measure preserving system given by the space Y, sigma algebra Cagliari Y, probability measure nu, and the measure preserving transformation S is loosely Kronecker if there exists a Borel subset A of the unit circle such that our initial system and the induced system maybe I'm sorry, this is A, lambda A, and are isomorphic. So a system, a measure preserving is a Kronecker system if we can see it as an isomorphic system to something which is an induced measure preserving as a measure preserving system induced by an irrational rotation of the circle. So this famous construction following the theorem of Poincaré allows us to say that whenever I have a measure preserving system and a measurable subset of a positive measure, then I can always take an induced system by just looking at the first return map to my measurable set, And this gives me a new measure preserving system, which we call the induced system. And loosely Kronecker systems is a class of systems which is obtained by looking at what can be induced by a single fixed irrational rotation. It's a part of a deeper theory saying that actually what kind of an irrational number we will take, or even what kind of a compact topological metrizable group we will take is not important. Up to the isomorphism, we will obtain the same class of measure preserving systems. And well, in the very end, I can announce the main theorem of our paper, that a topological dynamical system xt is a minimal, sorry, I need to assume minimal, is a minimal, is a topological model for a loosely Bernoulli system even only if it is rho fk equicontinuous. So in fact, this condition of the equicontinuity with respect to the pseudometric rho fk gives us the topological characterization of a class of measure preserve of topological models of loosely Kronecker systems. So this we find it quite interesting that actually we obtain characterization, because from the discussion I had with Till a moment ago, it follows immediately that neither equicontinuous systems nor mean equicontinuous systems characterize a class of topological models, because equicontinuous systems form a subclass of a class of all models of group rotations, and the same is about mean equicontinuous system. Mean equicontinuous systems form minimal mean equicontinuous systems. They form even larger class of topological models of group rotations. But in both cases, we do not see all possible models. And here in this theorem, we have first of all an intrinsic topological condition, meaning that, well, because what do you need to do if you want to verify that something is a topological model for some measure preserving system? So the definition asks you to actually leave your system, determine all its invariant measures, and check whether those invariant measures are, say, loosely Kronecker. So your verification that you are a minimal topological model for a loosely Kronecker system by definition requires some external external procedure. You don't see it from within the system. And this characterization is like gives you a purely topological description of the behavior of such model. You can think of it that you can now detect it from the inside by looking at the intrinsic properties of the system. You don't need to actually check what kind of measures and how many of them they are. So So this is one thing, and the second thing, it tells you that the loosely Bernoulli, the uniquely ergodic models of loosely Bernoulli systems are among many dynamical systems. They appear naturally. So our theorem gives you also in the other direction. It tells you something about topological behavior of orbits in such a model. So this kind of analysis applies to to horizontal flows, or any discretization of a horizontal flow, or to any uniquely ergodic interval exchange transformation. Because by a result of Katok, every invariant measure for interval exchange transformation has to be loosely Kronecker. Katok used the name standard, but this was due to the fact that at that time in the Soviet Union and in the Western world, this theory of classes of ergodic transformations was developed independently. So Katok in the Soviet Union and Feldman in the United States, they developed independently the same theory. And Feldman proposed names loosely Bernoulli with zero entropy. And I think Marina Ratner proposed to call those systems loosely Kronecker. And that's why we think that's the best name for those systems. And of course, I should write here loosely Kronecker. Okay. So I think that's a good moment to stop. I was planning to stop for 50 minutes, but yeah, it's after, I think that stopping after 48 is also okay. Thank you very much for your attention.
Okay, Dominik, thank you very much. Beautiful presentation.